While your computer wastes 99% of its energy as heat, a 20-watt organic machine in your skull performs quadrillions of operations, and we have finally figured out how to copy its blueprints into silicon. We are currently living through a period of unprecedented technological acceleration. Artificial intelligence has moved from a laboratory curiosity to the backbone of our global economy. However, this revolution has a hidden cost that we can no longer ignore. Every time you ask a large language model a question or generate an image, a massive data center somewhere in the world consumes enough electricity to power a small household for a day. We are hitting a physical wall, not of intelligence, but of efficiency. The architecture we have used to build every computer since the 1940s is fundamentally broken for the tasks of the future. This is the story of how engineering is moving past the era of ones and zeros, and why the next great leap in computing is not found in bigger GPUs, but in chips that breathe, pulse, and think just like you do. This is the rise of neuromorphic computing.
To understand why we need to rebuild the computer from the ground up, we first have to understand why our current machines are so incredibly inefficient. For nearly 80 years, we have relied on what engineers call the von Neumann architecture. In this design, the processor, which does the thinking, is physically separated from the memory, which stores the data. Every single operation requires data to be moved back and forth across a narrow connection called a bus. Think of it like a chef who has to walk across a giant warehouse to get a single grain of salt, walk back to the stove, and then walk back to the warehouse for a single pepper flake. This constant movement of data creates what is known as the von Neumann bottleneck. In modern AI workloads, moving data between memory and the processor consumes up to 200 times more energy than the actual calculation itself. We are essentially burning down the house just to light a candle. As AI models grow to trillions of parameters, the heat generated by this data movement is becoming a thermal barrier that even the most advanced liquid cooling systems can barely manage.
The human brain, however, does not have a separate processor and memory. In your brain, the processing and the storage happen in the same place, the synapse. Your brain contains roughly 86 billion neurons, connected by trillions of synapses. It is a massively parallel, highly distributed, and incredibly dense network. More importantly, it is asynchronous. Your computer's processor has a clock that takes billions of times per second, forcing every part of the chip to work in lockstep, consuming power even when it is doing nothing. Your brain does not have a clock. Your neurons only fire when they have something to say. They communicate using brief pulses of electricity called spikes. This event-driven nature is the secret to why the brain can perform complex pattern recognition and motor control while consuming less power than a dim light bulb. If we want to continue the AI revolution without bankrupting our energy grids, we have to stop trying to simulate brains on traditional hardware and start building hardware that is a brain.
This is where neuromorphic engineering enters the frame. The goal is not just to make a faster chip, but to replicate the physical architecture of the human nervous system in silicon. Instead of traditional transistors acting as binary switches, neuromorphic chips use specialized circuits that mimic the behavior of neurons and synapses. In these chips, memory and processing are fused. We call this in-memory computing. By placing the data exactly where the computation happens, we eliminate the von Neumann bottleneck entirely. There is no more shuttling of data across long distances. The energy cost drops by orders of magnitude. But the challenge of building such a system is immense. It requires a fundamental shift in how we think about semiconductors and how we write software. We are moving away from the rigid logic of Boolean algebra and into the fluid, probabilistic world of spiking neural networks.
At the heart of this shift is a device called the Memristor. For decades, we only had three fundamental passive circuit elements: the resistor, the capacitor, and the inductor. But in 1971, Leon Chua predicted a fourth element, the memory resistor, or Memristor. It is a component that can remember the amount of charge that has passed through it by changing its internal resistance. This is almost exactly how a biological synapse works. When you learn something, the connection between two neurons strengthens. In a neuromorphic chip, a memristor can store a weight, or a piece of information, as a physical state of the material itself. It does not need a constant flow of electricity to keep that memory alive.
This allows us to create high-density neural networks on a single piece of silicon that are thousands of times more efficient than the best GPUs on the market today.
As of June 2026, we are seeing the first generation of these chips move from secret research labs into real-world applications. Intel has been a pioneer in this space with its Loihi research chips. The latest iteration, Loihi 2, features up to 1 million neurons per chip and utilizes a specialized process node that allows for incredibly fast spiking speeds. Unlike a standard processor, Loihi 2 can process sensory information in real time with microsecond latency. Imagine a drone that can navigate through a dense forest at high speeds, processing visual data locally without needing a cloud connection or a massive battery pack. Or consider a prosthetic limb that can sense touch and react with the same speed and nuance as a human hand. These are the types of applications where neuromorphic hardware shines. It is not about replacing your laptop CPU. It is about enabling a new category of intelligent machines that interact with the physical world. IBM has also made significant strides with its North Pole architecture. North Pole is a specialized chip designed specifically for inference, the process where an AI model uses what it has learned to make a prediction. By integrating memory directly into the compute units and eliminating the need for external DRAM, North Pole achieves an efficiency that is staggering. In benchmark tests, it is shown to be 25 times more energy efficient than current 4nm GPUs, while maintaining significantly lower latency. This is crucial for the automotive industry. Self-driving cars require massive amounts of local processing power to make split-second decisions. Every watt of power saved by the computer is a watt that can be used to extend the range of the vehicle. Neuromorphic engineering is the key to making autonomous systems truly viable and sustainable.
However, the transition to neuromorphic computing is not just a hardware problem, it is a software problem. For the last half-century, every programmer has been trained to think in terms of sequential instructions and binary logic. Spiking neural networks operate on a completely different mathematical framework. In a spiking network, timing is everything. Information is encoded not just in the value of a signal, but in the precise moment a pulse occurs. This requires a new generation of algorithms and programming languages. We are currently seeing the emergence of frameworks like Lava, an open-source software framework developed to help researchers and engineers write code for neuromorphic hardware. We are essentially having to relearn how to communicate with our machines. We are moving from giving commands to designing ecosystems of signals. One of the most exciting frontiers in this field is the development of event-based sensors. Traditional cameras take 24 or 60 pictures per second, capturing every pixel in the frame even if nothing has changed. This generates a massive amount of redundant data that the processor then has to filter through. An event-based camera, inspired by the human retina, works differently. Each individual pixel only reports when it detects a change in light intensity. If nothing moves, the camera sends no data. When combined with a neuromorphic chip, this creates a system that is incredibly fast and efficient. It can track objects moving at thousands of miles per hour or operate in extreme lighting conditions where traditional sensors would fail. This technology is already being used in space exploration to track satellites and space debris with minimal power consumption. The engineering behind these chips also involves incredible breakthroughs in material science. We are no longer limited to just silicon. Researchers are exploring organic electronics, two-dimensional materials like graphene, and even phase change materials that can switch between crystalline and amorphous states. These materials allow us to create synapses that are even more similar to their biological counterparts. Some experimental neuromorphic systems are even using light instead of electricity to transmit spikes, potentially pushing the speed of AI to the limits of physics. The goal is to reach the density of the human brain, which has about 10,000 synapses per cubic micrometer. We are still a long way from that level of miniaturization, but the trajectory is clear. We must also address the philosophical shift this technology represents. For a long time, we viewed the computer as a calculator, a tool for crunching numbers. But as we move towards neuromorphic architecture, the computer becomes more of an organism. It is a system that learns from its environment, adapts to new data, and operates with a level of autonomy that was previously impossible. This brings us closer to artificial general intelligence, or AGI. If we can replicate the physical structure that gives rise to human intelligence, we may finally unlock the secrets of cognition itself. But we must be careful.
Building a machine that thinks like a brain means building a machine that might share our complexities, including our unpredictability. By mid-2026, the semiconductor industry is at a crossroads. The cost of shrinking transistors further is becoming prohibitively expensive, a phenomenon known as the end of Moore's Law. We can no longer rely on simply making things smaller to make them better. We have to make them smarter. The heavy hitters of the tech world are beginning to realize that the GPU-centric model of AI training is a temporary bridge, not the final destination. Companies like Rain AI are developing analogized NPU chips that promise to bring the power of a data center to the palm of your hand. These chips utilize in-memory computing to run massive models on tiny power budgets. We are seeing the birth of a new silicon stack, one designed specifically for the era of intelligence. As we look towards the end of this decade, the impact of neuromorphic engineering will be felt in every sector. In healthcare, wearable neuromorphic devices will monitor our vital signs in real time, detecting anomalies like heart arrhythmias or seizures before they happen, all while running for months on a single coin cell battery. In environmental science, thousands of tiny, low-power sensors will be deployed in forests and oceans to monitor climate change with unprecedented granularity. In our homes, robots will finally become useful, possessing the real-time processing power needed to navigate complex environments and interact safely with humans. The end of binary does not mean the end of the computer. It means the evolution of it. We are moving past the limitations of ones and zeros into a world of spikes, gradients, and temporal dynamics. We are finally bridging the gap between the rigid world of machines and the fluid world of biology. The engineering challenges are immense, from the fabrication of memristors to the development of new mathematical models for learning. But the prize is a future where intelligence is ubiquitous, sustainable, and deeply integrated into the fabric of our lives. The human brain is the most complex structure in the known universe. It is the result of billions of years of biological evolution, optimized for survival and efficiency. For the first time in history, we have the tools to translate those biological lessons into silicon and metal. We are no longer just building tools, we are building heirs to our own cognitive legacy. The brain-shaped chip is not just an engineering milestone, it is a testament to our desire to understand ourselves. As we continue to refine these neuromorphic systems, we are not just making faster AI, we are proving that the most advanced technology in the universe isn't a mystery, it is an architecture. And now we finally have the blueprint. The era of the von Neumann bottleneck is closing. The era of the organic machine has begun. When we look back at this decade, we won't remember the massive data centers or the energy crises. We will remember it as the moment we stopped trying to force the world into bits and started building machines that reflect the true complexity of reality. This is the end of binary, and it is only the beginning of what we can achieve. Engineering is no longer about fighting against the laws of physics to move data faster. It is about working with the laws of nature to create systems that think, learn, and grow. The silicon brain is here, and it is changing everything.